Good afternoon. Today what we'd like to do is we'd like to talk a little bit about supplementary materials. We'll continue our discussion from last class. Last class we talked about the materials and we said that there would be a few different things that we wanted to know about our supplementary materials. And anybody remember what those things were? They're going to convert bad things to good things, and the main bad thing that we're trying to convert is... All right, so one of the things that we want to do is we want to use our pozzolan plus calcium hydroxide plus what? Water. And we're going to be able to convert that over into our calcium silicate hydrate. This reaction tends to be relatively slow compared to some of the other reactions that are taking place. So that's part of our pozzolanic reaction. We said that there were some other aspects of a pozzolan that we should be aware of.
Intensifying action.
All right. Pozzolan would also have a particle filling effect. And this filling effect is mainly going to be for silica fume, and it's going to be because it is much smaller than the other particles. So pozzolans will typically be very, very effective when we look at them in the interfacial transition zone. They will be most effective in the interfacial transition zone, and it's mainly because of their size and the fact that they are going to react with calcium hydroxide. We said that there was another type of reaction that we could have with a pozzolan, and that was two types of reactions. One of them being a pozzolanic reaction, the second one being hydraulic. And we pointed out that we could actually look at a ternary phase diagram, and we could basically look at the ternary phase diagram. And we've got our alumina oxide down here. We've got our SiO2 up toward the top. We've got our CaO over here. We said that the closer that we get toward the top of this pyramid, the more likely it is that we've got SiO2. The more close it's going to be that we're purely SiO2, so it's going to be more pozzolanic. If we're down in this region down here, we've got something that's like an ordinary Portland cement. And as we move from an ordinary Portland cement up to SiO2, the types of reactions that are experienced are going to move away from being hydraulic into a realm where they're much more pozzolanic. What I want to do today is I want to finish up the discussion on the supplemental materials that we're going to be dealing with. And I want to talk a little bit about slag. We started off last class talking a little bit about slag, so I'll jump through some of the first slides very quickly. As we mentioned, slag is going to be very close to the ordinary Portland cement in terms of composition. So it's going to behave much more like a Portland cement than it is going to behave like a pozzolan. Slag replacements we will see will be very, very high. We'll see between 30 and 50% typically being used in a normal concrete application, going up to maybe 80% in some specialty applications like footings, mass concretes, dams, places where we're going to have a very large bulk of concrete being placed. So you can see on our ternary phase diagram that they're very close to each other, and they're very close to each other because of the way that they're being produced. We talked a little bit about the blast furnace, and we said that at the bottom portion of the blast furnace we were going to essentially be producing two main products at the bottom of the iron blast furnace. We have the material that people are really interested in who are in this process, and that is the iron. That's the molten iron. That's really what they're trying to take away. This is the material that's going to sink to the bottom. This is the pure material that they're going to go on to use to make steel or going to go on to use in an iron type of application. We have the waste material, which is typically just a leftover fluxing agent, the thing that was removing impurities. And this is the slag that we are going to be talking about utilizing during this portion of the class. It's really a waste product from the iron industry. So it's a byproduct of the blast furnaces that are used to make iron. It is a mixture of iron ore, coke, and limestone. Typically, it will come off as a molten liquid, and it is viewed as a waste material. It will float because it has a lower specific gravity than iron. Iron will tend to sink because it's heavier. This will have a specific gravity that will cause it to float on top of the molten iron. And we will jump through. It'll be drawn off of that iron at regular intervals. So here you can see it in its molten state. It will essentially begin to flow off of the top. And the usefulness of it depends upon the structure that the material develops. So last class there was a question that was asked related to, are there any other potential applications for slag? And one of the things that will dictate where slag gets utilized is how fast it is cooled. If it's cooled very, very rapidly, then it will be used to make an amorphous material that's really reactive, and this is what we want for cements. So if it's cooled very, very quickly, it will not have time to form as crystallized a structure. It'll be much more reactive, and this is beneficial for a material like cement that we want it to be very reactive. If it's cooled more slowly, it will develop a more crystalline structure, and this is typically what we'll see being used as slag aggregates or materials like a lightweight aggregate or a slag aggregate, because it's not going to be as reactive. As mentioned, the rate of cooling will determine how amorphous the material is. The faster it's cooled, the less structured, the more amorphous it's going to be, the more reactive it's going to be. And this gives you a little bit of an idea of the glass content or how amorphous the structure is versus how much strength it's going to gain at 3 days. You can see the more rapid it's going to be, more rapidly it's cooled, the more glassy it's going to be, the higher the strength is going to be. Now, one of the ways that they will try to cool it this quickly is they will actually spray it with water jets as it's coming out of the, as the liquid slag is coming through the machine. So you'll see here the liquid slag being drawn off. It'll hit a deflector plate. There will typically be a water jet that hits it very quickly. That water jet may have some other things in it other than just pure water to try to cool the material down very, very quickly. As it is cooled down very quickly, it will get the type of structure that we're interested in, and then the material can be segmented depending on how big the particles are. They will fly out to different distances, and that's one of the ways that they can segment and keep these materials separated. Once it is cooled very quickly, the material will be ground. Much like we saw with a normal Portland cement, it'll be ground in one of these big grinding mills with steel balls being dropped on top of it. One of the things that I will point out here, and this is one of the things that is often confusing, people will say, well, slag, why would it be as expensive, or why can't it be as expensive as Portland cement? One of the reasons is because it's going to be harder to grind. The slag tends to be a harder material. It'll take a little bit longer and a little bit more energy to grind than a normal Portland cement. Typically it will be ground to something that's a very similar fineness, although we'll talk about a few of the other options in a couple seconds. But most of the time it's going to be ground to something that's very similar to Portland cement. Slag distribution, this is a slightly old map, so there'll be a lot of different slag grinding facilities. You'll see a lot more have opened up in the west. Typically they'll be bringing in slag from the Far East to meet demands of those markets. ASTM C989 is a specification that you'd want to be you want to be looking at. That should be ASTM, and it'll be based on a slag activity index. And the slag activity index is simply the strength of the slag material over the strength of a Portland cement times 100% at a specific age. So if you're looking for a 7-day slag activity index, it's basically giving you how does this material develop strength compared to an ordinary Portland cement. A slag activity index of 100 means it's the same as an ordinary Portland cement. 80 means it's going to gain strength a little bit more slowly. 120 means it's going to gain strength more rapidly. These numbers will be typically relatively fixed in a particular market. So if you're in a market, you'll probably only be able to get one type of a slag activity index because they're not going to grind. It's not like Subway where you can go and get the sandwich any way you want it. They grind the slag in one particular fashion, and you're going to get a slag that is pretty typical to that area. Most of the time you're looking at something with a slag activity index of about 100, so it's very, very similar, very comparable to the normal Portland cement. Specific gravity for these materials, slightly different than Portland cement, but you'll notice it's not that far off, 285 to 29, where we know our ordinary Portland cement has a specific gravity of 315. Okay. Typical dosage rates for slag, as I mentioned before, 25 to 50% will be somewhat typical. You will also see it being used at a little bit higher dosage rates. In some applications, paving 25 to 50%, flat work 25 to 50%, footings you may say a little bit more. When they get into mass concretes, you'll see they start to get up to some of these numbers that are very, very high, 50 to 80% of the Portland cement being replaced with slag. As I mentioned last class, there'll be ways that you can activate this. Typically, the alkalis will help to activate the overall system. There'll be chemicals that can mix in to sort of kick off this reaction very quickly. The types of things that are going to influence how fast the reaction is going. The chemical composition of the slag is going to be incredibly important. The alkali concentration, whether it's coming from the slag, if you're adding the alkalis in an activator, or if it's coming off of the Portland cement, will be important. How glassy the slag is, how fast it was cooled, how fine it is, how much it's ground. And then one of the other key issues, and we'll see this as we keep coming back to this, and we'll talk a little bit more when we talk about early age concretes and curing, especially with supplementary materials. They can be very sensitive to changes in temperature. They're more sensitive typically than a ordinary Portland cement to a change in temperature. So a lot of times you'll hear people, oh, we tried to do this on a cold day, or we tried to construct on a hot day and we got very different results. It's like anything else. You need to get used to it. Once you get used to it, you can understand what steps need to be taken to get a normal hydration rate, get a normal strength development process going with these materials. Slag, again, much like Portland cement, it's going to undergo a hydraulic reaction, which means when it comes in contact with water, it's going to react. So you want to keep your slag from getting wet. All right, just like Portland cement, you wouldn't leave it sitting out in the rain. You can't do the same thing with slag. Color and fineness are going to be very similar to Portland cement. It's handled very much the same way Portland cement is. Should be weighed after the cement. You'll find this with most of the supplementary materials. That way, if something happens to stay on the scale, you'll have the Portland cement in the system. These tend to be smaller amounts. Activator, you may use something like a sodium hydroxide or sodium chloride. This will accelerate the reaction of the slag. Water demand will be somewhat lower, maybe 3 or 5% lower. And it's becoming more and more popular. You'll see people using a ternary system. Slag is one of the binders that they would like to use in a ternary system. And when we talk about ternary means three-part system. So a lot of times you'll see Portland cement, slag, and then something else being mixed in, and a lot of times that something else is going to be silica fume. So they'll be using silica fume, slag, and cement all together, and they can be very beneficial. Mike?
You said it can't be wet, but when they spray it with the water jet, where does that water go? Does it evaporate right away because it's so hot?
Yeah, that water will just be used to quench the material, and then they'll go on and they'll process it from there. They'll have to grind it. The main thing is once it gets into a fine powder, you don't want it to be wet because it's going to be just like a Portland cement.
So at that stage,
it doesn't matter. Right.
The water will make a difference.
Right, because you're going to create a whole lot more surface area once you start grinding it up. Right. As I mentioned before, it's important to remember that your set times may be altered. And your early strength development may be altered, especially when you have very cold temperatures. So it'll behave a little bit differently than Portland cement, have a different activation energy, so the rate will change. So it may be much more susceptible to a 30-degree Fahrenheit temperature than a Portland cement is, and you need to be aware of that. Typically, a rule of thumb is the saw cut is delayed for about 30 minutes for 10% of slag, and I would say this rule of thumb is a very general rule of thumb because it depends a lot on how fine the slag is ground, what else is in the system, but it will slow down the overall process of setting the overall construction operations that are taking place. Mechanical properties are going to be very similar to your ordinary Portland cement. The paste will become a little bit more dense. Again, we've got a supplementary material that's undergoing a pozzolanic reaction as well as supplementary. And the other mechanical properties are typically very similar. Durability, a lot of times you can see the permeability decreasing because this material will react more slowly over time. We're filling in more of the pore space. You'll also see improved resistance to sulfate attack and alkali silica reactivity, and this is mainly because we're going to have a reduction in the alkalis in the system, and we're going to change the permeability of the system. We're going to densify the overall system. You'll also see that slags can bind chlorides, so when we talk later on in the semester about salts, either from the ocean, salts coming in from deicers, they will tend to not only be slowed down as they go through the system, but the slag will want to grab onto them and hold onto them. So what you'll see is a lot of the chlorides will actually be bound before they can get to the reinforcing steel when you've got slag in the system. Freezing and thawing is generally very similar. One of the other things that I will mention here, and we'll come back to this, A lot of the materials that we will talk about that have supplementary materials will show a problem with scaling, especially in the lab. This is the top surface, the top film of the concrete coming off when it's exposed to freezing and thawing and de-icing salts. You'll see that top thin surface will pop off. If you go out in front of the civil engineering building, you'll notice that it looks like somebody exposed all the aggregates for that 100-foot strip on the mall as you walk down on the what is the front side of the building, but the back side of what everybody approaches. You'll notice that the aggregate surfaces all look like they're polished. That is a scaled surface. The Portland cement covering that was on top of them came off with de-icers. This will be very problematic in the lab, but a lot of times this same response is not seen in the field, and it has to do with a problem with the lab test is very, very sensitive to just about everything. It's a very small section. It's very sensitive to how the surface is finished, where you don't see that type of sensitivity in field applications typically. So the lab test can make this material look much worse than it actually is in the field. As mentioned before, it will help in mitigating alkali-silica reactivity. This is an aggregate that will react with the alkalis that are coming off of the cement. The main idea here is the alkalis will actually react with the slag. They'll actually participate in the reaction, so they'll reduce the overall alkalis, so they will take them out of the system. They'll also reduce the size of the pores, and they'll make it harder for things to flow through the system. One thing that is kind of intriguing about slag that's sort of interesting, and this appeared in one of the recent Concrete Internationals yet again, and I've got it listed as on sort of a Kermit the Frog theme. Many of you may remember Kermit, and Kermit had a problem because he used to sing about it all the time, that it wasn't easy being green, and when he was down on himself. Slag concretes are very intriguing, that many times when you take them out of the molds initially, they will look green. You can see this picture here. You see the greenish tint. One of the first times that I used slag and I demolded it, I also had a little bit of latex in the mixture, and it was not just a little bit green. It looked like it was St. Patrick's Day green. One of the things that I will point out is if you're ever on a job and this occurs, you see the surface turning green. It's actually the sulfide sulfur in the slag that's reacting. Typically when this touches the atmosphere, dries out a little bit, that color will go away. It will stay this funny bluish green color, however, if you seal it immediately. So what you typically want to do if you see this happening is allow it to get exposed to the atmosphere for just a little bit of time. That color will go away, and then start applying your sealer. Main benefits. Here we have a curve that we've seen before. And where have we seen this curve? Where were we talking about this curve?
Hydration.
This is our heat of hydration curve. So this was our rate. This was our dq dt type of curve, where we were basically saying this is the rate of reaction that's taking place. This is the rate at which heat is coming off. What you will notice is that when you have 100% Portland cement, this peak that occurs in the third and fourth regions is very high. As you start to add slag to the system, you will notice that this peak shifts down, and it also shifts a little bit to the right. That's completely explainable with the fact that the slag will react at a slower rate. So that's why we're seeing it shift to the right. There's also a lot less heat being generated, and this is what you will see as one of the big benefits of seeing this type of material used in mass concreting. For more information, here's a few places that you would want to take a look. 2 ASTM standards. ACI 223 is the committee that deals on slag, and AASHTO M302. The next supplementary material that we want to talk a little bit about is fly ash, or fly ashes, because there will be different types of fly ash. This is probably the most common supplementary material or pozzolanic material that's being used, and is a byproduct of the coal production industry. So ground coal will be used in an electrical power plant, and this is the leftover material, the leftover coal that didn't burn, and what we're trying to do is utilize that so that it doesn't need to be landfilled. Recent surveys have said that this is used in up to about 50% of the ready-mix concrete that's out there. You are seeing a much bigger push for this to be used because there is a lot more fly ash that can be used, and this is a great way to start utilizing it. It tends to be spherically shaped, so you can see a picture of this up close and personal. There will be two different types of spheres. One type is a hollow sphere One type is a solid sphere. Again, the sphere is forming because this is being produced as it's going up the chimney. It's a liquid. It begins to cool down and become a solid, and the size that has the lowest energy is a sphere. There will be two main types of classes of fly ash that people want to talk about: Class F and Class C, and they will be designated by how much calcium they have in those mixtures. We'll talk about that a little bit more on the next couple of slides. Fly ash replacement, again, to give us a little bit of an idea of where it falls on our ternary diagram. We've got our Portland cement down here, about a third of the way up on our CaO SiO2 line. We saw slags, which is what we were just talking about, being right in this region here, slags. And then as we start to move up, we will go through a Class C fly ash. As we move even higher, we'll get to a Class F fly ash before we ultimately get up to where our silica fume is. This is a material that is pozzolanic. Obviously, Class F is going to be more pozzolanic than Class C. Class C will have a little bit of its own hydration or hydraulic capabilities on its own because it's got a little bit more CaO in the overall system.
Diagram. As we go up to SiO2, it's more pozzolanic reaction, and back to CaO, it's a hydraulic reaction. Is there any other type of reaction if you head towards the aluminum side? Is there a name for that type? Yeah, you could actually get a pozzolanic reaction taking place in that direction as well. So you could actually, we're going to talk mostly in this class about the silica materials, but you could also have an alumina type material that could be pozzolanic as well. But we're not going to get into that because there's not a whole lot of commercial products. Name to go that way?
Nope.
Okay.
Sorry. And it's not a special. I can make one up if that helps.
Oh, okay.
It could be the Norfleetian reaction as it goes this way. How's that sound?
Sounds good.
Okay. But these are just sort of general properties of these materials. Okay. And the main reason that it becomes more pozzolanic is because you've got more SiO2 in the system. And it's the silica that's really the main component that we're after. The materials, again, they're going to be similar in size to the cement. So they're going to be roughly the same size distribution. Now, there is one material that's out there that's a little bit different than this. And you will hear there's a specific company that markets it as an ultra-fine fly ash. This is basically them taking and using basically like a cyclone or a centrifuge to get rid of the big particles and keep only the small particles. Why would they want to keep only the small particles?
Reaction.
Oh, we got lots of different answers there. Or maybe they were all the same answer. Higher surface area. So if it's smaller particles, it's higher surface area. Higher surface area means it's more reactive. So what they're really looking to do by getting rid of the big particles is to make a material that reacts more quickly, because one of the knocks on fly ash is it will delay the rate of hydration. So what they're actually trying to do is make it smaller than cement, much like we saw with silica fume. They're trying to get a reduced particle size. But that's a very specialized form of fly ash called ultrafine fly ash, and it's typically going to have an extra process, centrifuge or something like that, to try to separate out the particle sizes. Most of the time, we're only differentiating the materials based on their CaO contents, and this is going to be mainly the difference between the C and the F ash. Byproduct of the coal and electrical power plants. It will be a finer portion of the mineral coal impurities. They will melt. They will go up the chimney. They will recrystallize when they're hit with an airstream. And then they will be caught in something like the world's largest shop vac, an electrostatic precipitator in the bag house that will take this dust out of the air, and then we will start saving it and start trying to figure out where it's going to be used. So here's the basic idea. The coal will go into the power plant. It will essentially be burned up. As it goes up through the chimney, you'll see this material, these impurities will be captured so that the air that comes out is going to be a little bit more pure. 50 million tons of fly ash is produced in the U.S. Annually. You will notice that around the world, this 50 million tons is a tiny number. You see the numbers that people are talking about in other countries that burn coal. The numbers are staggering, how much fly ash they're producing. 10 to 12% of the fly ash that's produced in the U.S. and Canada will find its way back into concrete. Some of this fly ash that's not utilized is not utilized for a reason, because it has properties that make it not that beneficial. A lot of times there'll be materials that are added to the processing to try to make the air even cleaner that mean that it can't be used again in concrete very easily. But there's still quite a big percentage of this that could be increased if there was really the market for it and people would be really excited about using it. I mentioned a lot of times you'll hear people talking about the scrubbers on these plants. These scrubbers are trying to make the materials more clean, and a lot of times they'll mix some of the fly ash with free lime and calcium, and that's where it really becomes non-useful, and most of the time those materials are being landfilled. Southern Indiana, there's a few plants that do this. All the people who send you your energy bill are very excited about this. The electric company that you pay, they have big fields of this material with the scrubber cake that's actually been mixed in with the fly ash and can't really be reused. Since about the late 1960s, early 1970s, the plants that are producing fly ash have become really much more cognizant on quality control. So the fly ash, even though it's a byproduct, the fly ash is really consistent and will have a finer particle size than what was seen earlier on. Here are the main places where coal is coming from. You will notice that the coal is going back to where it's coming. All right, I stole this off the web, and every so often it just disappears. You'll notice that in the southern part of Indiana, as I mentioned, there are some big coal deposits here that we are typically very interested in looking at. The different types of coal that are burned will actually change whether it's a Class C or a Class F fly ash. Most particles are solid spheres. Not all, but most of the particles are going to be solid. They're going to be spherical, and they are referred to as plerospheres. Partially hollow, thin-walled spheres are called cenospheres. You can impress everybody tonight by asking them if they know what a cenosphere is or a plerosphere. If it works, let me know. I'm not sure that that's really a great way to introduce yourself to new people this evening, but you can give it a whirl if nothing else is working. Class C fly ash, high calcium ashes. They are typically going to be coming from the coals that are west of the Mississippi, and typically we're talking about things that are greater than 20% CaO. Class F fly ashes, low calcium ashes, going to be higher up on the ternary phase diagram, and typically we're looking at things that are coming east of the Mississippi rivers. They're going to have mostly clay type materials that are their impurities. You can go through here and look at all the different types of properties. A few of the things that I really want to focus in on: the specific gravity or the densities of these materials. Specific gravities are going to be a little lower than what we've been talking about up to this point, somewhere between about 1.9 and 2.8 for the fly ashes that we're using. Most of the time they're going to be very similar in size to the cement particles. I'll let you go through and pull out a lot of these other materials. They were originally used mainly as a replacement. In many places they will be much, much cheaper than Portland cement. Some places, depending upon availability, they may be similar in price. Right?
Looking at the gravities there, looks like there's a lot larger range than it is with slags. Is that a quality control issue, or is that just the difference between C and F?
It depends a lot on how much of the C and how much of the different types of coals they're burning and what their process is on burning. As I mentioned, in the 60s and 70s, we said that the quality control really improved. Well, the quality control was part of what improved. What actually was the main driver improving it, they were burning it more efficiently. So they don't really do quality control on the byproduct. They're really trying to make it more efficient when they're burning it. And right as they went into the energy crisis, they really improved the overall efficiency. So now you also have people, though, that are monitoring what's happening, and they're not switching the coals. They're trying to burn it consistently so somebody could actually use the byproduct. Generally, the material will be spherical. So this is my artistic rendering of fly ash here up on the top, and my artistic rendering of cement. Cement will be jagged type particles because it's crushed. The fly ash will be more spherical particles, so they will be a little bit easier to move in the forms. They'll be a little bit more flowing. They will respond a little bit better to vibration. So typically you'll see the water demand will go down. Easier to pump Typically, you'll hear people talking about the cohesiveness of the mix being improved. Because of this, they'll have a little bit less segregation and a little less slump loss, especially in hot weather. As mentioned, you will also get a delay in set time here because the fly ash is not reacting as quickly as the Portland cement. You will also notice one of the biggest things, and I will point this out here. We'll talk about this briefly in a second. One of the biggest problems with using fly ash or quality control on fly ash is looking at the dosage rate for your air entraining admixture. One of the big things that people get very worried about with fly ash is how much carbon you have in that fly ash, because carbon, some of you will know who have air filters at home, or you've got a roommate who's running that air filter constantly. One of the best types of filters that you could put in an air filter is a charcoal-based filter. Carbon type filters. These carbon filters will actually have quite a bit of internal surface area, and they can actually absorb the air entraining admixture, which if they absorb the air entraining admixture, it's not there to do what it is to do in the mix. So if you have a lot of variability in the carbon content, you'll have a lot of variability in the amount of air you need to get air in your particular concrete. So you can have a lot of fluctuation when we start to talk about chemical admixture use. So one of the biggest things that we'll see people talking about doing quality control on here is really looking at the carbon content in the different fly ashes.
Is that exclusive to air entraining admixtures, or is that kind of for all admixtures?
It's a lot of admixtures, but the one that people get most excited about is air entrainers, because that's the one that they're typically required to have on most concretes, and that's the one that people are typically checking most frequently. One of the ways that you can look for the carbon contents in these materials is a loss on ignition test. This is basically taking the fly ash, looking at the weight of it, taking it up to a much higher temperature, like 750 degrees C, looking at how much of the material is burned off, and that will tell you how much of the material is lost when it's heated, lost on ignition, and that'll give you an indirect measure of the carbon content. Pretty good estimate of the carbon content, and gives you an idea of how much air entrainer or other admixtures might be consumed. Typically, we're interested in the particle sizes. We will talk about this later on in the semester, very similar to cement. One other test that you can do to see its ability to interact with air entraining admixtures is a foam index test. You can read through here, but the basic idea is you take a little bit of the fly ash, a little bit of the air entraining admixture, shake it up, and see how long it keeps a nice frothy head on the fly ash, cement, water, air entrainer admixture, and that tells you a little bit about how much carbon is in the overall material. So I've got all the steps here, so you don't necessarily have to go out and look for it, but I'm not going to go through that in real great detail. Mechanical properties, there really aren't a whole lot of big differences in the mechanical properties. They will tend to gain strength a little bit more slowly. Generally, elastic modulus, similar. Strength is going to be similar. Creep and shrinkage are going to be similar. They will improve a little bit of the long-term durability by reducing the pH, and they will tend to reduce some of the ASR problems because they will take some of the alkalis out of the system. Freezing and thawing, the main thing that they're going to alter with freezing and thawing is obviously how effective the air entrainers are. So we put air entrainers in to provide space for pressure to be relieved during freezing. If that is all sucked up in the carbon that's left over inside of the fly ash, it's not going to be as effective. So summary of some of the differences. Remember, physically the big differences that we have in addition to size, we have cement and slag that are going to be crushed. So they are going to have irregular shapes. They're going to have a lot of surface area. We have fly ash and silica fume, which are going to tend to be more rounded. Silica fume much smaller than fly ash. Fly ash is very similar in size to our Portland cement. So here you can see a little bit of their size distribution. You'll notice that things like our Class C, our Class F, and our cement are all relatively typically in the same size region. Something like a metakaline or a calcined clay might be a little bit smaller. And then we've got silica fume that's way over here on the right-hand side. Most of these materials will be similar or slightly slower than our normal Portland cements. Environmental friendly aspects of this are incredibly important. If we don't have to put materials through the kiln to produce the same amount of binder, We've substantially reduced the amount of CO2 that needs to be liberated to make the amount of concrete. So there's a substantial improvement in sustainability by using things like fly ash, using things like slag, using things even like bypassing and putting limestone into the mixture. We'll talk a little bit more about this at the end of the semester when we start to talk about sustainability issues. Many of these materials will be less expensive than the cement that they replace. However, one of the things that you need to keep in mind, there is typically extra quality control that needs to be done and extra grinding on these materials that need to be done, and that's a price that will come into the overall process. Questions on SCMs before we jump ahead and cover about 12 minutes of water? Okay. So as I mentioned today, the entire lecture was dedicated to water, but we need about 10 minutes to cover water, and we'll probably have about 2 or 3 minutes of that left over by the time we're all done. Water is it's really one of the big paradoxes in concrete. One of the things that's kind of interesting about water is we obviously are going to need it to cause the reaction that takes our calcium silicates into calcium silicate hydrate. But water is also one of the biggest principal agents or the enemies of concrete, because it's going to be one of the things that's really responsible for degradation. So if we think about a lot of the types of ways that concrete can fail, if it fails due to freeze-thaw damage, if it fails due to alkali-silica reactivity, if it fails due to corrosion, if it fails due to shrinkage, there's typically an aspect of this that has water really right at the forefront. Freezing and thawing, if you don't have water inside of the concrete, that water can't freeze and expand, can't cause the problems that we have with freezing and thawing. So water is directly responsible there. Shrinkage is typically dictated by the loss of water in the system and the volume change that takes place as water leaves the hardened cement material. ASR, water needs to be present to move the alkalis throughout the system. If the system is dried out, you can't get ASR reactions taking place. You no longer have a problem. Corrosion, again, you need to have water that's going to be moving our chloride ions through the system. So again, water is a principal aspect here that's leading to the transport of materials that will take place in the deleterious reaction. So water is going to be both essential, but if we have too much water during mixing, it's going to be a problem because it's going to make our concrete porous. If we have too much water later on, it's going to lead to some other degradation problems. Here you can see a pretty severely freeze-thaw damaged parapet on a bridge. Here you can see someone actually using fine concrete making techniques here to mix up their dried cement powder and aggregates in a very controlled fashion. Basically, the biggest rule of thumb in what makes concrete good to be used, what makes water good in concrete, if you can drink it, it's usually pretty good. So I wouldn't say that this is the first test that I would do if I didn't know about the water source, but generally the rule of thumb is if you can drink it, it's pretty good. What I will also point out is there are a few other things here. Funky water, water that you may not want to drink, may also be okay too. It all depends what's in the water and what's causing it to be funky. If it's green algae or something like that, there could be some issues. If it is water that you might even want to drink that it maybe has a lot of sugar in it, that could cause its own problems, and we'll talk about that in a second. Generally, though, most of the water that you're going to experience in the U.S., most of those water sources are going to be okay for manufacturing your concrete. You can get into some problems if you're out west and you may have some water that's sitting, or you may have some other issues. But generally, we've got good sources of water. You can use them to make your concrete. Now, one of the things that I find that's one of the most intriguing aspects here of water really doesn't have a whole lot to do with concrete, but it has to do with one of the products that I found when I was spending time as a visiting professor in Japan. And there were vending machines, like we have Coke machines, that were dedicated to selling Pocari Sweat. And it really begs the question, what is Pocari Sweat? And a Pocari could be one of these small little animals. You could no, Pocaris are not small little gerbil-like animals that are on wheels. that actually produce Pocari Sweat. This is something that's very similar to Gatorade. I think it's a very odd naming convention, but I think this is something that you should take with you as you leave. Many of you will be working internationally. You may want to check the words that you're using internationally with people who speak the language to find out how attractive Pocari Sweat may be to people more familiar with the U.S. language here. I didn't find it that tasty, even not knowing that it was Pocari Sweat. I sort of got past the name. I tasted it just for the pure scientific aspects of it. It really tasted like Gatorade without a lot of flavor to me. So the Pocari will now go off into history. Again, it's a lot like weird tasting Gatorade, and there are huge numbers of machines that are dedicated to this. Bad water is mostly going to cause strength development problems. A lot of times what you'll find out is the bad water will actually get in and interfere with the reaction taking place. The other things that you need to worry about, you need to worry a little bit about water that's going to be containing salts could take part in corrosion, and water will also alter, and you could get staining or efflorescence because of what's present in the water. Main thing, though, is you're going to alter the setting time, and you could lead to deleterious reactions. Big thing that you want to make sure of when you're starting to look at water, you want to make sure it's really free of organic materials. If it's free of organic materials, you're typically not going to see a big impact on the setting time or strength development. One of the simplest tests to do if you think you have water problems, you can test the strength development of concrete that's made, or mortar cubes that are made with DI water versus the water that you may have locally. Typically, it's believed not to be a problem if you're starting to get strengths that are about 90% of what they were without with the local water. If the local water is 90% of what you get with the DI water that you could pick up at the local Walmart, then you're in pretty good shape, and it's probably not a water issue. As I mentioned, the main things that you're going to be wanting to look out for is any alkalis that may be in the water, any sulfates that may be in the water, and specifically when you start to deal with places that are near the coast, any chlorides that might be inside of the water. Chlorides have a little bit of a nebulous history in concrete. For many years, chlorides were actually put in to accelerate the strength development in the concrete, but this is a big no-no because it's going to also accelerate the corrosion. And there are several buildings that are undergoing corrosion problems because someone put it in as an accelerator. Seawater, typically it's a big no-no to put seawater into your concrete. Again, we were talking about this. The chlorides in the system will cause freezing and thawing damage. So save your seawater for swordfish capture or something like that. Don't put it in the concrete unless you figure out a way to deal with the chlorides that are in the overall system, or if you're producing concrete that doesn't have reinforcing steel. If your concrete has no reinforcing steel, then you can probably get away with using some chlorides in the system. Chlorides, again, you've got the potential for accelerated corrosion, specifically a big problem in pre-stressed concrete because the steel is under a constant stress. It's more likely to corrode more quickly. You can also see some of these issues when you've got aluminum embedments. A lot of times you'll see this on balconies that may be overlooking the ocean or something like that. They'll put an aluminum pocket inside of the concrete. Aluminum is a material that's reactive on its own with concrete, so it'll actually bubble up and form sort of blisters, aluminum blisters. You can also have problems that are due to corrosion. Chlorides will come not only from water, you'll also see them in some of the admixtures, you'll see them on some of the aggregates, you'll also see people adding them in accelerators. Mainly this will happen toward the late fall construction time. You'll see people wanting to put in accelerators, and you'll see a big distinction in accelerators made between accelerators that contain chlorides and accelerators that don't contain chlorides because of this problem with corrosion. Again, some general rules of thumb. ACI 318 tells you how much chloride can be in your overall mixture by mass of cement. The easiest way to solve this when we start to talk about water is keep the chlorides out of the water, and you're in good shape for that. And then look at where the other places where the chlorides may be coming into the mixture. Algae and organic material can alter both air content because it can basically do what we were talking about before, the carbon doing with your air entrainer. Can either suck up that air entrainer or can make it not work as effectively. You'll also see that the strength can go down when you've got a lot of these algae and organics in the material. You can see sort of uncontrolled air contents as well with some of the algae and organics. So you want to make sure that you're not getting a lot of algae, pond scum, tadpoles, anything like that in the water that you're using inside of the concrete. Sugars will alter set. Sugars will reduce the set, if not completely kill the set. So if you take a 1 pound bag of sugar, throw it in the back of a ready-mix truck, you can pretty much make the concrete not set. And this is a big issue. So if you see a ready-mix truck driver who's got a bag of sugar under the seat in the front, that's in case he gets stopped in traffic. He can basically take it up, throw it in the back of the truck, and you're not going to fill a drum full of hardened concrete. You would get concrete that would just never set or take an enormous amount of time to set. Similar types of things you can do with Pepsi if you really wanted to. You can dump some Pepsi in the back of the truck. The sugar in the Pepsi will slow or just kill the entire reaction process down. You want to be real careful with sugars. Sugars can come in not only from water, if you had water that may have some sugars in it, but you can also get sugars from things like cellulose fibers, or different types of wood fibers, or different types of natural fibers may have their own sugars in them, which can cause problems in setting.
You throw the sugar in, does it have to be in before final set or before initial set, or is it just before final?
Typically they would be throwing it in before initial set, but it usually, if you're mixing it, then it'll stop. It gets mixed in, it'll stop the process. Typically it's before initial set, because once you get toward initial set, it's pretty tough to be mixing it in, because you're getting something that's pretty stiff. Alkali carbonates and bicarbonates, sodium, it'll accelerate the reaction. Potassium hydroxide will accelerate the reaction. Again, you just want to keep an eye on this, because not only will it accelerate the reaction, but it can participate in a reaction with the aggregates down the road that can be detrimental. Silts, you want to try to keep silts out. You want to make sure you're using quite a bit of settling basins. Sulfates will cause expansive reactions. You typically want to limit the amount of sulfate that's inside of the water, limit some of these other materials down here. Here's a general typical city water. What you might get here is a typical seawater, the types of chemical analysis that you might get. This is out of the Design and Control of Concrete Handbook from PCA. One thing that I will point out is they have a pretty big range of what may be typical. So you want to make sure that you don't just look at one particular sample and say, oh, we've got something that's really a big problem here. There's a pretty big range of what may be taking place. One of the things that I will point out that's sort of a very hot issue right now is the idea of reusing water that's coming out of concrete. There's a big push to try to make concrete more environmentally friendly, and one of the things that they're trying to do more frequently is to reuse the water that goes into washing out the truck, and reuse the water that comes from when the truck goes back to the plant. So a lot of times you'll hear a lot of discussion on reusable mixed water. One of the big issues is if you're washing something down, it's not only going to have whatever's in the water that was there originally, it's going to have whatever was coming off of the cement, whatever admixtures might be there. So typically you can use the water from the washout as long as it meets these criteria. And typically they're really worried here about your chlorides, your SO4, and your solids. Those are the things that they're mainly interested in. Here you can see trucks. They'll be washing out, and then they're basically running the water through a series of cyclones. The idea here is to take out some of the solids and to get back to a point where they've got something that's a little bit cleaner water. Typically what they'll do is they'll give the water time to settle out some of the solid particles and then try to reuse some of the water. The big questions now are how to economically dispose of wastewater and unused concrete and still comply with the increasing environmental constraints. So there's a lot of research and a lot of efforts that are going on into how to more effectively reuse water, or more effectively put the concrete to sleep. When you get a half a truck full of concrete that comes back at the end of the day, can you put it to sleep and then wake it up again tomorrow morning so that it's a fresh concrete that could go out to a different job site? There's a lot of work that's going on in this. I will say that Japan has a mandate where they really try to reuse all the concrete. They claim that they have zero waste coming out of the industry. This is something that the U.S. is becoming more and more aware of, especially in urban environments, and is one of the big changes that you'll probably see taking place over the next 10 to 15 years. Mainly here they're looking at the recycling problem. As I mentioned, there's a lot of ways that they will maybe put the material to sleep. Typically these will be referred to as stabilizers, where they'll drop an admixture in, it'll stabilize the system, and then they'll add another admixture the next morning that'll wake the whole system back up again and make it so it'll go back into reaction. Here is something that I had the opportunity when I was in Japan to see. This was them not only reusing the wastewater, but they would actually reuse this sludge, and they had built a plant that looked something a lot like a kiln, where they would actually take this leftover sludge, they would throw it back through the kiln, make it a reactive material, and then really be reusing it. So a review of mixed water in the last 10 seconds. Water is a key, hydration and degradation. You want to remove any impurities. The biggest things that you'll be looking at are deleterious reactions and setting time. Most of the time, not a big issue. Any questions?